So there's this mathematical theorem that proves it is literally impossible to write a perfectly fair algorithm.
Yeah, which is a pretty heavy thought to start with.
Right.
Yeah.
But, I mean, tonight, there are probably thousands of engineers staring down their IDEs trying to do exactly that.
Oh, absolutely.
And if you're listening to this, you are probably one of them.
Yeah.
You know, you're deep in a late-night coding session hunting down logic bugs, and usually those bugs are, well, they're predictable.
Yeah, like a null pointer exception or a race condition.
Exactly.
Yeah.
A memory leak. You can trace the stack, find the flaw, and just fix it.
Ah.
But welcome to the deep dive. Today, we are getting into the evaluation module from the LLM Mastery Notes. Specifically, we're tackling bias and fairness. And we aren't hunting null pointers today. We're tracking down bugs in society that get compiled right into the weights of a neural network.
Yeah, and it fundamentally challenges how we architect systems because, when we talk about bias in AI, we're actually talking about human history. Human assumptions, societal structures, all of it just being crystallized into matrices of weights and biases. We're dealing with inherited state on a massive scale.
Inherited state. I like that. And that inherited state is usually where the conversation sort of derails.
No, definitely.
Like when an AI system does something blatantly unfair, say an image generator just straight up refuses to show female CEOs, or a resume parser downgrades applicants from certain zip codes.
Which happens a lot.
Yeah, the default engineering assumption is that it's just a localized data bug, garbage in, garbage out. The thought is just, oh, someone fed the model a bad CSV file. Let's just scrub the data set and retrain.
Right, which, to be honest, is the most dangerous oversimplification in machine learning.
Really, the most dangerous.
I mean, yeah, because bias doesn't just sneak in through one bad data set. It's integrated into the AI pipeline at every single stage of development. We're talking about data collection, the labeling, model training, the evaluation metrics themselves, and ultimately deployment.
So fixing the raw data while ignoring the rest of it is...
It's insufficient.
Okay, let's unpack this with, like, a software analogy. Or, actually, no, let's use a physical one. It's like plumbing.
Okay, plumbing. I'm with you.
Imagine your water filtration system. If the pipes coming in, the filter itself, and the tap are all slightly rusty, just changing the filter won't give you clean water.
Right, the rest is everywhere.
Exactly. You can't just clean your data set and call it a day because the whole system is corroded.
That is a much more accurate way to look at it. And what's fascinating here is when you trace that rust through the pipeline.
Yeah, how does that actually look?
Well, start with data collection. You might build a web scraper that unconsciously pulls from forums that are, heavily skewed toward one demographic.
Okay, so the pipes are rusty from the start.
Exactly. But then it moves to labeling. You hire human annotators to classify the data, and those humans possess subconscious biases.
Right, because they're humans.
Right. So they might label ambiguous text as, say, aggressive when it's written by one demographic, but they might tag the exact same phrasing as assertive when written by another.
Oh, wow. Yeah, so the rust just compounding. And then we hit the training phase, which is where the math actually works against you, doesn't it?
It really does.
Because the objective function you define is usually trying to minimize overall loss. The algorithm just wants to get the highest accuracy score possible across the entire data set.
Precisely. So think about it. If a specific minority group only represents, say, 5% of your training data, the model's gradient descent is going to treat that group's unique features as noise. The math actively penalizes the minority group because optimizing for the 95% majority yields a lower global loss.
Oh, so it's not even a mistake from the algorithm's perspective.
No, the model is mathematically incentivized to ignore the edge cases to boost its overall score.
It's just doing what you told it to do. It's optimizing.
Exactly.
And then you get to evaluation, where you test it against a holdout data set. But if your holdout data set has the same skew demographic distribution as your training data, your test will just pass with flying colors.
Yeah, it's a complete echo chamber, which means by the time you reach deployment, you are pushing a deeply flawed model into a real-world workflow where it will systematically fail specific users.
So it requires a total paradigm shift for engineers.
Yeah, you have to move from viewing bias as this localized data bug to seeing it as a systemic end-to-end architectural failure.
Okay, so since this bias is leaking from every joint in the pipeline, what exactly does this rust look like when it actually reaches the end user?
Well, the notes break this down into 3 specific types or faces of bias.
Right, representation bias, stereotyping, and allocation bias.
Oh.
Let's dig into the actual mechanics of these, starting with representation.
Sure. So representation bias is essentially about who is entirely absent from the feature space.
Absolutely.
Think of a speech recognition model trained almost entirely on audio clips of people speaking with West Coast American accents.
So if that model hears someone from Glasgow or, I don't know, Mumbai or the Deep South.
It completely hallucinates.
Wait, really? It just breaks.
Yeah, because it lacks the dimensional mapping for those phones.
Yeah.
The acoustic features of a Glaswegian accent simply do not exist in the model's latent space. To the algorithm, the user doesn't just sound different.
They effectively don't exist.
Exactly. It's a failure of inclusion at the most fundamental level of the vector space.
It's the AI equivalent of a blind spot. But stereotyping operates differently.
Right.
Stereotyping is when the people are actually in the data, but the model's mechanics have linked them to reductive attributes.
Yeah, that's a good way to put it.
How does that actually happen under the hood? Like mathematically?
It comes down to how large language models map words in n-dimensional space using vector embeddings.
Okay.
LLMs learn by predicting the next word based on vast amounts of internet text, right? They calculate the statistical proximity of words. Right.
So, if the text it ingested overwhelmingly pairs the word doctor with male pronouns, the vector for doctor is pulled physically closer to the vector for he and him in that multidimensional space.
So it's almost like a gravitational pull.
Exactly. The internet's historical bias creates this gravitational pull between certain concepts. So when you ask the model to translate a gender-neutral language, like Turkish, into English, the model calculates the vectors and forcefully applies those gendered assumptions.
It translates it to he is a doctor and she is a nurse.
Yeah, because mathematically, that is the path of least resistance based on its embeddings.
That's fascinating, but, as an engineer building a product, the third type, allocation bias, that feels like the real danger zone.
Oh, it absolutely is.
Because stereotyping and representation, those are the underlying mechanics, but allocation bias is where the system actively draws a boundary that denies someone a service. Is that the most dangerous one? I would argue yes, because allocation bias is the tangible consequence in the real world. It's where the mathematical decision boundary directly impacts a human life.
Let's walk through that. How does the decision boundary create allocation bias? Say we're building an automated loan approval model.
Okay, good example. You train a classifier to predict whether an applicant will default on a loan.
Oh, wait.
The algorithm draws a complex hyperdimensional line that's the decision boundary separating the approve applications from the reject applications.
Makes sense.
But the algorithm is just looking for patterns to minimize risk. If the historical data shows that people from specific zip codes had higher default rates, perhaps due to decades of systemic redlining and underinvestment, the model uses zip code as a heavily weighted feature.
And it draws the decision boundary right around those neighborhoods?
Exactly.
So even if a specific applicant in that zip code has flawless credit, the model's boundary sweeps them into the reject pile just because it correlates the geography with risk. It allocates an opportunity unfairly.
It is a direct degradation of service. And because the model is a black box, the applicant is simply told, computer says no.
With no actionable recourse.
None.
Man, this brings up a massive issue for anyone currently writing test coverage. Let me put my engineering hat on for a second and play devil's advocate here.
Okay, go for it.
Let's say I'm writing a rigorous CI/CD pipeline. I write a unit test that enforces demographic parity for race, meaning the model must approve loans at equal rates for black applicants and white applicants.
Okay.
Then I write another completely independent unit test that enforces parity for gender-equal approval rates for men and women.
I see where this is going.
If my pipeline passes both of those tests, shouldn't the model be mathematically fair? Like if A is fair and B is fair, my system is solid for everyone, right?
That is the most common logical trap in machine learning evaluation.
Wait, really?
Yeah. What you just described leads directly to the intersectional blind spot. The math breaks down because human identity does not function like isolated independent variables in a clean equation.
But wait, if my aggregate metrics show 90% accuracy for white individuals, 90% for black individuals, 90% for men, and 90% for women, the dashboard is entirely green.
It is.
Are you saying my passing pipeline is hiding a catastrophic failure?
If we connect this to the bigger picture, yes, I am. Because an algorithm can achieve parity on the aggregate level while masking severe disparities at the granular level.
How does that work?
Let's look at the confusion matrix for your hypothetical loan model. You have equal accuracy across the broad categories. But if you dig into the intersectional data, the overlapping realities of those identities, you might find that the model is 99% accurate for white men, but only 60% accurate for black women.
Oh, so the high performance in one intersection is balancing out the failure in another.
Exactly. The math averages out to 90% across the broad categories. Your single variable unit tests passed because they asked a fundamentally flawed question. You asked the test, is this fair for this isolated feature? But the model doesn't experience a user as a single feature. It processes the user as an intersection of features.
So the test isn't technically lying, it's just answering the wrong question.
Exactly.
So if I don't write my test to explicitly evaluate the intersections, like evaluating every permutation of race, gender, age, socioeconomic status, the model will quietly fail the most marginalized users, and my log will never explicitly tell me why.
You will never see it unless you explicitly look for it. Intersectional evaluation is mandatory if you want to understand how your model actually performs in the wild.
All right, so I see the problem. I need to map out the intersections. But, the engineering instinct here is to say, okay, we just need to tune the math.
Right.
We take all these intersectional groups, we define what perfect fairness looks like, and we just adjust the objective function so that the accuracy, the allocation, the representation is perfectly balanced for every single group. We just optimize our way out of it.
And this is where we hit the most sobering realization in the entire field of AI.
Uh-oh.
You cannot optimize the math to achieve perfect fairness for everyone. It is mathematically impossible.
Wait, I want to make sure I'm hearing this correctly. You are saying we literally cannot write perfectly fair code.
I am saying it is a mathematically proven theorem. It's called the impossibility theorem of fairness.
Okay.
It proves that you cannot simultaneously satisfy all reasonable, mathematically sound definitions of fairness at the same time. If you optimize your algorithm for one metric of fairness, you mathematically guarantee that you will violate another metric of fairness.
Here's where it gets really interesting. Okay, for everyone listening who deals with distributed systems, think about the CIP theorem.
Oh, that's a great comparison.
The CIP theorem, consistency, availability, partition tolerance. You can only ever have 2 out of the 3 in a distributed database.
Right.
If a network partition happens, you have to choose. Do I keep the system highly available but risk serving stale data to the user? Or do I enforce strict consistency and make the system completely unavailable until partition heals? You can't have all 3. You have to choose your trade-offs.
The impossibility theorem functions exactly like the CAP theorem, but for machine learning. Let's walk through the numbers so you can see the math breakdown.
Let's do it.
Imagine you're building a predictive policing model, or let's go with a healthcare triaging system.
Okay, healthcare.
You have 2 groups of people, Group A and Group B. Let's say there are 100 people in each group.
Okay, 100 in A, 100 in B.
You decide you want your system to be fair, so you choose a metric called demographic parity. This means the model must output the exact same proportion of positive predictions for both groups.
Got it.
So if it selects 30 people from Group A for an intervention, it must select exactly 30 people from Group B.
Makes sense. Equal rates for equal groups. That sounds like fairness.
But what if Group B actually has a historically higher underlying base rate of the condition you are testing for?
What do you mean?
Let's say due to systemic environmental factors, 50 out of the 100 people in Group B actually need the healthcare intervention, whereas only 20 out of the 100 in Group A need it.
The baselines are different.
Exactly. So if you force the math to achieve demographic parity picking 30 from both groups, look at what happens. For Group A, where only 20 people need it, you are selecting 10 people who don't need it.
That is a massive spike in false positives.
Right. And for Group B, where 50 people need it, you are only selecting 30. You are actively leaving 20 sick people behind. That is a massive spike in false negatives.
Wow. So by enforcing demographic parity, we just denied healthcare to a huge chunk of Group B.
So you look at that and say, well, that's terrible. Let's change the math.
Right, obviously.
You decide to optimize for a different fairness metric called equalized odds. This metric demands that the false positive rate and the false negative rate must be identical for both groups. You don't care about the total number of people selected, you just want the error rates to be perfectly balanced.
Which means the model is equally accurate for both populations.
Yes. But because the underlying base rates are different, 20 in A versus 50 in B, to get the error percentages to match perfectly, your model will have to select a vastly different absolute number of people from each group. It might select, say, 15 from Group A and 45 from Group B.
And the moment it does that, we have completely violated our first rule, demographic parity. We're selecting 15 versus 45. The rates are no longer equal.
You literally cannot have both. The math forbids it. If the underlying base rates of two populations differ, which in the real world they almost always do because of historical inequities, you are forced to choose.
So you have to pick your poison.
Yeah. Do you want demographic parity, which skews your error rates? Or do you want equalized odds, which completely destroys demographic parity?
This raises a massive point. This fundamentally shifts the role of the software engineer. Because if you cannot mathematically satisfy all definitions of fairness, then choosing which definition of fairness to prioritize is no longer a technical decision.
It is a moral decision.
Let that sink in. If you are writing that code, you're not just building an algorithm anymore. You are encoding a specific moral philosophy into a production system. You're deciding whose definition of fairness wins out. Are you optimizing your model to protect the business from the cost of false positives? Or are you optimizing it to protect a marginalized user from the harm of false negatives? You have to pick one, and gradient descent will not make that choice for you.
This raises an important question about how we build teams, actually. This is why fairness in AI cannot be solved purely by engineers working in isolation.
Right. You can't unit test your way out of a moral dilemma.
Exactly. It requires domain experts, ethicists, and representatives from the communities being impacted by the system to help define what the appropriate trade-offs should be for that specific use case. A healthcare system will require very different trade-offs than a marketing recommendation engine.
So what does this all mean for the listener? This is heavy stuff, especially if someone listening right now has a sprint planning meeting tomorrow morning.
Yeah, reality check time.
If perfect, mathematically sound fairness is a literal impossibility, what does a responsible engineer actually do tomorrow? Do you just throw your hands up, ship whatever you have, slap a beta label on it, and hope for the best?
The first practical step is accepting that reality. Bias-free AI does not currently exist.
Period.
If a vendor tries to sell you an enterprise model and claims it is 100% bias-free, they are either lying to you or they fundamentally do not understand the math.
Probably both.
Right. So the goal of responsible engineering in this era is not to achieve mythical perfection. The goal is relentless vigilance.
Moving from the illusion of perfection to the practice of vigilance. I like that. What does that actually look like in a repository, though?
First, it looks like extreme transparency. When you evaluate your model and inevitably discover intersectional blind spots, you do not bury those metrics.
You document them.
You document the limitations clearly. You publish them in model cards so that downstream developers and stakeholders know exactly where the model degrades. If your facial recognition system drops in accuracy for older women of color, you document that failure openly.
It's treating bias like a known architectural limitation rather than a dirty secret. Like, if an API has rate limits, you document them. If a model has demographic limits, you document them.
Exactly. Secondly, vigilance requires continuous measurement. You do not just evaluate for bias once before launch and call it a day.
Because data drifts.
Data drifts, user behavior changes, the internet's gravitational pull shifts over time. You have to build telemetry into your pipeline that continuously monitors for allocation bias in real time.
So we need to be setting up the equivalent of data dog alerts, but for fairness metrics.
That's a great way to think about it.
Like, if the false negative rate for a specific demographic suddenly spikes in production on a Tuesday afternoon, the system needs to trigger a PagerDuty alert immediately.
Precisely. And the third step, which is arguably the most critical for high-stakes decisions, is designing for human oversight. You build human-in-the-loop workflows.
Right.
If your AI is determining medical diagnoses or mortgage approvals or parole recommendations, the system must be architected to flag ambiguous or high-risk cases for manual review. The algorithm should augment human judgment, not act as an autonomous judge and jury when the stakes are irreversible.
This has been a massive shift in perspective. We spent this entire evaluation module from the LLM mastery notes dissecting how we measure systems. We've talked about measuring output quality, we've covered testing for hallucinations, and today we've mapped out the pervasive pipeline of bias. We've looked under the hood at how vector embeddings create stereotypes, how decision boundaries enforce allocation bias, and we ran headfirst into the hard mathematical wall of the impossibility theorem.
It is a dense set of concepts to synthesize, for sure, but it is the necessary foundation. because everything we have discussed so far has existed within the theoretical, somewhat sanitized realm of evaluation and research.
We've been looking at test data.
Right.
But the next phase changes everything. Next time, we are leaving the lab. We are shifting gears entirely to deployment. We are going to look at what happens when your carefully evaluated model leaves the staging environment and slams into the messy, chaotic, unpredictable reality of production systems.
That is where theory meets traffic.
Exactly. The transition to deployment is where all of these theoretical fairness metrics face their ultimate stress test. Real-world users interact with models in ways developers never anticipate.
It's going to be a fascinating breakdown.
It really is. But before you get back to your code, before you close that terminal window and call it a night, we want to leave you with one final thought. We spent a lot of time on the impossibility theorem of fairness and how choosing a fairness metric, deciding who absorbs the false positives and who suffers the false negatives, is fundamentally a moral decision.
Right.
So here's the question you need to ask yourself. Look around your office or scroll through your team's Slack channel tomorrow morning. Who on your engineering team is actually getting to make that moral choice? And more importantly, what exactly qualifies them to make it?
Good luck with your deployments.
Catch you on the next deep dive.